Okay, welcome back, all of you, to this faculty development program. Now, in the first session, I like to introduce Professor G.L. Samuel, the invited speaker of this session. Professor Samuel is presently working on manufacturing engineering section of Department of Mechanical Engineering at Indian Institute of Technology, Madras. Professor Samuel has received his PhD degree from IIT Madras in 2001. He was worked as a postdoc fellow in Kyungpook National University, South Korea. He has then joined IIT Madras as faculty in 2005, and since then he is serving in different capacities there. Presently he is serving as a professor. He has also served as guest faculty in the University of South Carolina, Charlotte, USA, and as visiting faculty at Politecnico di Milano, Milan, Italy, and Deakin University, Melbourne, Australia. Professor Samuel has done extensive research in the field of advanced manufacturing technologies involving micro and nanoscale technologies. He has published authored several papers in peer-reviewed scientific journals and books and book chapters. He has several granted patents and acted as invited speaker in several scientific events. Okay, so and moreover, he is also involved with different industrial projects and consultancies. So with this short introduction, I like to invite Professor Samuel to deliver his lecture. Sir.
Yes, sir. Thank you very much, sir, for the introduction. Before we go into the lecture, so you're all teachers, isn't it? So I would like to interact a bit with you. So can some of you at least please introduce yourself? Yeah, I'd just like to understand what is your background so that I can pitch in my lecture in the right way. Yeah. Yeah, you can unmute and speak. Sir, hope you have given the permission for them to speak, isn't it? It's all unmuted. They can unmute?
Yes, sir, we can hear you.
Yeah. Okay, Mr. Sumit Shah. Which college you are from and what are you doing? Just few of you. You can just unmute and speak.
Sir, hello, sir.
Yeah.
Hello, sir. Good evening, sir.
Yes. Yeah, good evening.
Sir, I am Atul Potode. I am from Sipet. I am working in Sipet. Hello, sir. Hello. Sir, is hello.
Yes.
Hello, sir. Is I am audible?
Yeah. Yes, yes.
Yeah. Yes, sir. I am Atul Potode. I am from Sipet, Haldia.
Hello, sir. Hello.
Yeah.
Hello.
Myself,
Yes, yes.
myself, Dr. Devashish Das Adhikari, Associate Professor, Mechanical Engineering Department, Haldia Institute of Technology.
Oh, okay. Yeah, thank you, sir. Thank you. Yeah, some more people?
Hello.
Yeah.
Good evening, sir. I am Dr.
Yeah, good
Deepak Kumar Mondol. I am Dr. Deepak Kumar Mondol from College of Engineering and Management, Kolaghat, head of the department. I am from the same district of Haldia Institute of Technology.
Oh, okay.
I am working mostly, I am from the thermal engineering department. but I do some work for microfluidics also.
Okay, okay, sir. Yeah, thank you. So we
Thank
have a
you,
lot
sir.
of senior people attending. Yeah, good.
Yeah, yeah.
Mhm.
Yeah, yeah. Thank you, sir.
Yes.
Hello,
Yes.
this is Dr. Ashish Mitro from Kolaghat Engineering College.
Okay.
I did my PhD degree in on experimental heat transfer, natural convective heat transfer.
Mhm.
2002, I awarded PhD degree from
Mhm.
that experimental research work. Now I am
Okay.
doing some numerical research work on heat transfer in base fluid and nanofluid.
Okay. Okay. Good. Good. Yeah. Thank you.
Thank you, sir.
Okay.
Good evening,
One
sir.
more.
Good evening, sir.
Yeah. Good evening.
Sir, myself Sanjeev Sandhaki. Sir, presently I am working in Mitsubishi Chemical Corporation, Haldia. Actually, after completing my diploma in mechanical engineering, I was
Mm.
in the steel plant in Raurkela in mechanical department as a trainee engineer. After
Okay.
that, in 2006, since then, now I am working as assistant manager, Department of Utility,
Mhm.
and so I have give the I have the opportunity to be a part of this in this training program. So I'm very much grateful to all of you and eagerly waiting for your speech, sir.
Okay. Thank you, and welcome you all for this short-term training program.
Thank you, sir.
Uh,
Thank you.
yeah. So we are going to now look at the topic which is called ultra short pulsed laser micro machining. So this is the topic I have selected. And before going into the details about the ultra short pulse laser micro machining, we are going to talk about the micro machining, and then we are going to look at some of the applications so that you can understand. So in the inaugural talk itself, professor has very clearly told about the various applications and other things and why these micro nano technologies are important. So I'd also like to reiterate that, and then we are going to move forward into the laser micro machining. Yeah, 1 minute. Professor Gautam, I think we have the facility to record. So maybe if you can record the lectures, so that will be useful for the future. Or maybe some students or participants are missing, they can see the video.
সাইজ ওই 1 ঘন্টা হলে ইয়ে হলে ক্যান্সেল করে এটা আমি তুলে নেবো হার্ড ডিস্ক নিয়ে অন্য নতুন করে দেবো।
Yeah, who is controlling this? Who is the admin for the Google Meet?
Yes, sir.
Yeah, can you record? You can actually record all the lectures.
Yes, yes.
So we also conducted the program and then we recorded it so that if some participant miss or if they want to look at them at later stage,
Yes, yes, sir.
they can do that.
Yes, sir. We are recording this session. We are recording, sir, this session.
Yeah. No, you have already started recording or you're going to
Yes, sir.
record?
No,
Sir?
we have already started recording.
Oh, but it doesn't show up here.
We are making the screen recording.
Okay, fine. No, but yeah, that's okay. Fine then. Okay, so we'll proceed.
Yes, sir.
Yeah, as we have been hearing about the micro machining. So why this is important? So if you look at the present world scenario, there are two types of technologies which are becoming very, very important. On one side, it is macro, and on the other side, it is micro and nano. I'll tell you an example. See now, if you look at the aircrafts, so there are aircrafts or even UAVs, unmanned vehicles, so which are as small as like an ant or a bird or an insect. So that is the scale. But on the other side, we see that there are huge aircrafts as big as the football court. So if you look at the jumbo jets, so when you look at their wingspan, so when you put them in the football ground, so the wings from tip to tip, it will be the width of the football court. So as big as that. And also when you look at the ships, so you can make the big ships, so as a huge as a tiny city, you can make that kind of a big. And at the same time, we have the products, so which are so tiny. Thus, today's technologies are on two extreme sides. One is on making the scale bigger and bigger, but on the other side, it is micro and nano. So as for the theme of this conference, so we are looking at the micro and nano side of the manufacturing and the technologies. Now, these miniaturized technologies, if you look, so they are playing a very important role, not only at present, but also they are important in the coming days. So why this miniaturization trend is very important is that, so by miniaturization, we can reduce the amount of energy which is used, the amount of space which has been used, so and the noise which is produced we can reduce. So thus we have a lot of advantages when you scale down the product. I'm going to give you some of the examples in my lecture, so where we can understand how this miniaturization, micro and nano scale manufacturing has completely revolutionized the way how things were made and how we look at manufacturing. As Professor has already tried to define what is this micro machining or micro manufacturing or micro nano scale. So usually when we make a product or a feature, I think you may understand what is a feature, like a circular hole. If you make, that is a feature. Or if you make a micro channel or a channel, that is a feature. So thus we can either make a 3D structure, a device, a moving part, or a feature which is in the order of micrometers. So initially, when they defined micro machining, they said anything below 1 millimeter is micro. But now we find that the scales are coming down. So then later, after a few years, even when I started with the micro machining, they used to say it is sub-micrometer is micro, all the sub-millimeter is micro scale. But then later they said that is too big. So let us reduce to 500 micrometers. So then now people are moving, so telling that even 500 micrometers is large. So we'll even move down to 100 micrometers or so. So thus, it's always, we find that the scales have been coming down and we are able to make the products in meso. Rather, the scales can be put like micro, meso, sorry, macro, meso, micro, and nano. And then later we are going to move on to the angstrom units. So this whole idea was started with a very visionary kind of a term. So where Richard P. Feynman, he made a statement right in 1959. So telling that there is plenty of room at the bottom. There is plenty of room at the bottom. So when you look at 1 millimeter, we thought that is the whole limit. So in 1959 and all, they couldn't even think about the technologies what we have today. But still, Feynman, he said that there is a lot of room below. So then he started defining what is called as the micro, nano kind of a scales. So he said that, why can't you write the entire 24 volumes of Encyclopedia Britannica on the head of a pin? So this You can't even imagine that he told this in 1959. So after probably half a century and more, so now it is becoming a reality. It is becoming a reality. So thus there were visionaries. So we have seen long back itself that these type of machines and products are going to come. And one something more interesting, when you look at these micro machining technologies or nano and all, you know what is the inspiration? It is actually the nature. It is the nature. When you look at this bird, sorry, an insect, which is a small wasp. So this is the picture. If you go to YouTube, I think there's a link, but I'm not going to show the video. So you can go there, and when you look at the video, you can understand that when it want to lay the eggs, so it will have a string, so the tail, so which has a tip. So that tip is very sharp, and they try to understand what is that material, and they found that it is like a zinc. Then it will vibrate with a high frequency, then drills the bark of a tree, and then lays the egg there. And also here there is fluid mechanics which is coming. This tail, usually it will be very flexible, but then when it pumps the fluid, it becomes stiff, and then when it vibrates, it will be able to drill. So thus, what we are talking about now, micro machining and all, was there in the nature right long back. And also, one more interesting thing, what we find in the nature is that the insects, this insect, so there is a small name for this insect, which has the only mechanical gates ever found in the nature. And the size is, you can see here, 20 micrometers. So just 20 micrometers. That means the whole length could be like 150 or 200 micrometers. So in that, they have a mechanism. So this insect, actually, when it wanted to jump forward, so it has a mechanism like a micro gates, so where they will clutch like this, and then they move and gives the impetus for the insect to jump for a longer distance than what it is capable. And you can see the tooth profile and the whole set of teeth with the gap and everything. It has been so nicely made. Okay, so this article came in Scientific American. So if you want, we can actually look at this article. So thus, it is the nature which has inspired the micro and nano technologies, and the visionaries have thought about this kind of thing, not today, but even half a century ago. So why this micro machining is important, as I have already mentioned. So the efficient utilization of space. I'll give you an example why this is true. Then saving of energy and material resources, reduction of vibration and noise, then easier control of waste and pollution, then reduced capital investment. But as of now, we find that the micro and nano scales are more expensive, but once the technology is mature, the cost actually will be coming down. Then improved portability, so we can actually carry the product, so that has become possible. And then the higher speeds. Okay, before I move on, I'll ask you a question. Since you're all teachers, so you would have seen the machine spindles, okay, which will be rotating, maybe in a lathe or a milling machine or in a grinding machine. So what is the RPM of these spindles? Turning, milling, and grinding. Yeah.
Ines, this question is for machines or?
Yeah.
Sir, this question is for CNC machines.
Pardon?
RPM, you are asking about RPM. Hello?
Yes.
Sir, you are asking
Yeah.
about RPM. Sir, is question is CNC machines
Yeah.
RPM. So in the CNC case, it may be vary, sir. It's depend upon our requirement. The RPM is it's depend upon our requirement. It's it's depend upon my conditions.
Yeah. Can you give me a number?
We select the RPM.
Yeah.
Uh, Maximum or minimum, sir. In case, we can use maximum RPM also, and we can use RPM.
Okay. What is the maximum RPM which you have seen?
Uh, uh, Maximum RPM last capacity.
Yeah. Anyone else? What is the highest RPM which you have seen? Is the voice clear?
Yeah.
Let me just turn off. I think we hear some kind of disturbance. Yeah. Yeah. Anyone else? Can you say what is the maximum RPM which you'd have seen in practice? Can you type in? Yeah.
তো ম্যাক্সিমাম আরপিএম কত জিজ্ঞেস করছে ও বোধহয় ভাবছে যে ওর নেটের প্রবলেম হচ্ছে শুনতে পাচ্ছে
11,000. Yeah. Anyone else? $5,000. Grinding?
$1,000 to 1,500 RPM.
Speed of the grinding wheel. 1,500. Okay. Yeah. So can you imagine anything rotating at high speed? So what is the maximum speed anything can rotate? What you have seen in your life or heard?
And drones about 10,000 RPM.
Oh, that's all? Or anything more? Yeah, you have heard about turbo machines, no? What will be the speed?
I am going to I don't know, but the turbo machines like for the jet, the speed will be maximum, I think, for the jet plane.
Yeah, what is the speed?
I cannot say, but at this moment, but maximum speed will be there.
Okay, so what can you can just guess some number?
About 20,000.
Okay. Yeah. See, can you imagine that we can have the turbo pump which can rotate at 2 lakhs RPM?
Oh my
Have you
God.
heard about that?
Oh, no, sir. 2 lakhs RPM.
Yeah, 2 lakhs RPM or even 2.5 lakh RPM. See, if you look at the utility vehicles, so maybe you would have heard this term, what is called as turbocharger. Okay. So in the utility
Turbocharger.
vehicles, on the back side of the vehicle, it will be written as turbocharged. So that means they have a turbo pump which rotates at 2.5 lakhs of RPM. And that is possible because of this miniaturization. The size of it will be very small. The Q or the
Oh,
discharge of it will be very small, but the speeds will be very high.
very high.
And in
Oh,
our IIT Madras, here we have a machine. It is called ultra high speed machine tool. So where the spindle will rotate at 1.6 lakhs RPM. I'll repeat, the spindle speed is 1.6 lakhs RPM. Can you imagine?
oh.
So that is actually possible. So thus, only when it is in the micro scale or when the particles are small, we'll be able to achieve that kind of a high speeds. So thus, micro machining is the technology. So wherein it helps us in very high speed technology. So otherwise, if you take a big gear or a turbine pump and try to rotate with that speed, probably it will break into pieces. But with help of micro turbines, micro pumps, we'll be able to rotate it at that high speeds. So then moving on,
স্যার এই একজন জয়েন করতে চাইছে বলছে। হ্যাঁ হ্যাঁ
just a minute. Oh, these are all the pains we used to have during the lockdown. So network and then it gets struck, kind of thing. So sorry for that. Yeah, can you give an example which is the best for miniaturization? So what are the practical, you have been looking at so many products. Can you say which is the best example for miniaturized product? Yeah. Can you give the example? Which is the example, best example for miniaturized product? Are you able to hear?
Yes, sir. I'm
Sir.
trying just. I don't know how I'm right or wrong, sir. Whenever we discover the computer system, there we have the cassette. After
Yeah.
that, the compact disc were discovered, CD.
Yeah.
Then some floppy. Now, sir, pen drive. So
Yeah.
this is the development of the technologies, and we get the product of the miniatures.
Okay, fine. So yeah, thank you. But one product you have forgotten, which everyone uses and every day nowadays. Without that, you will not be able to be there. So what is that? What is that? Yes, mobile phone. So you're right.
Smartphone. Yes, smartphone.
Yes,
Yes,
phones So if you look at the picture here, this is not a supercomputer, but this is the first computer, so which was made in 1950s and 60s. So it was 1946. So when they were using this, the power consumption for one computer was 160 kilowatts. And then when one computer is turned on, the whole city lights used to come down. So that was the first computer. But then later, if you look at the chips and the processors and what all these technologies which have developed, so the sizes have come down, and nowadays we see that the sizes are very small, but the computers are very, very powerful in processing the data. And cell phone is another very important example for the miniaturization. So this was the Motorola company, so which made one of a kind of mobile kind of phones. So we can't call them as mobile, but the military, they used to use it, they used to carry to communicate between the troops. And by the way, do you know who invented this mobile? And you can see the picture of the person also. Everyone carry mobile phone, isn't it? But do you know who is the person who invented it? You can type in the answers if you need.
Sir, Martin Cooper.
Yeah, very good. So Martin Cooper is the one who invented it, or rather the technology is attributed to Martin Cooper. So thus, because of that miniaturization, so nowadays we can know that either from a city to a nook and corner, so the mobile phones have reached, and everywhere you can see people using it. So thus, the miniaturization, the portability have very much increased because of the miniaturization trend. But also you can see one of the products here, an interesting product. It is called mini petrol engine. So where you see this one, so they have made a small petrol engine which you can hold on the fingertips or nail tip, and there if you fill few drops of petrol, so it can run for about 10 years. So thus this is an example for the consumption of energy with a minimum consumption of energy when you use the product. And why they have made this kind of a product is that, so in the watches, what we wear, what we wear, so the quartz watches, so if you use them for 1 or 2 years, the battery actually fails. So we may have to change the battery. But here they want to plan the product in such a way that once you seal, put few drops of petrol or diesel and then seal it, so it will run for 10 years, almost like the lifetime of the watch itself. So thus there are several products which are possible because of this miniaturization. So there are micro channels, fiber optic wires with a micrometer diameters, and then we have the holes which have been used in automation of the diesel. So the smaller these holes, so the more efficient will be the combustion. So nowadays it is possible to make the holes even much, much smaller. And also when you look at the mechanical watches, so they have been made so precise that they go fast or slow, even just few seconds per year. So that's the way how they were able to machine these kind of components. And also, as I have been talking about the turbines, so flying turbines, so where they can even rotate at 1.1 million RPM. That means almost like 11 lakhs RPM. So these are all possible when you make them smaller. So if they are big, probably they will just crush into powder. But when you make them small, they'll be able to rotate at these kind of high speeds. And also, when you look at the micro gears, so by MEMS technology, micro electromechanical technology, so you'll be able to develop these gears, so where they are so small and the power which is required to drive them will be very small. So thus we don't have to lose a lot of energy or spend a lot of energy, but with minimum energy, we'll be able to make the product to work. And also there are trenches or micro channels with a high depth by using which we can make microfluidic devices. So probably if you look at the product which is being used for detecting the coronavirus, so they had a portable kit. I think in the second wave and later, many of them, they never wanted to go to hospital, but they want to test themselves. So they had this kind of a kits. So they are called as the microfluidic devices. So where there are micro channels, micro chambers in which the tests were conducted. As even the professor has been mentioning a term called lab on a chip. So that means we can make several tests on a chip, which is the size of an ID card. So thus, these are all possible because of miniaturization. And not only that, you'd have heard about what is called as painless injections. It's because the diameter of the injection is small. If it is big, we'll feel the pain. Then laparoscopic surgeries and pinhole surgeries. So pinhole means you make a surgery, but only make a small hole, insert the devices, and then carry out the surgery. So thus the recovery time is very fast. So after the surgery, maybe the same evening they can walk and come, even after making a big surgery, but with a small hole. And there are devices which are called as blood filters. So where if there are fat particles in the blood, so they put these kind of filters before the blood enters into the heart, and we can filter out the fat particles which are higher or bigger in size when compared to the regular blood cells. So this is an example for the lab on a chip. So this one actually we have machined it right in our IIT. So the one which is there on the left side, sorry, on the right side. So where we can make the chambers, we can make the micro channels, and then we can carry out several tests in all these chambers. Then there is an interesting actually product which you have seen. So we have that machine called as a Kern machine tool, which is an ultra high precision, high speed machining, high speed machine. So where the spindle rotates at 1.6 lakh RPM, and they use the conventional tools up to the diameter of 30 micrometers, and the hair diameter usually will be around 100 micrometers. But here, the hair which has been used for this machining is the secretary of the company called Kern Machine Tools. So it is in Germany. So usually women have a thinner diameter hair, and Europeans have the thinnest, Africans have the thick hair, Asia and Middle East smaller size, and then Europeans even thinner hair. So thus they could take 60 micrometer hair, and then they could machine a 30 micrometer hole. So thus this is actually, you may ask, what is the application? It is a technology demonstration which is possible these days. And actually, everyone are familiar with the jet engines. So jet engine is one of the most complicated product which have been developed by engineers in the present, in any time in history. So this is the most complicated one, and the reliability what we are looking is the highest. Why? Because if it fails, so many of the lives will be at stake. And nowadays actually we have 2 jet engines which are mounted on the wings, and then even one fails, if the pilot has the skill, he can drive them and bring it to safety. But still, the highest reliability has been expected from these jet engines, and they are very complicated. And in this, the temperature which is there inside this combustion chamber is higher than the melting temperature of the turbine blades. So that means literally, if you don't do anything in this combustion chamber, all these blades should melt away. But they don't melt because they use three kind of technologies. So first one, they coat them with what is called TBC, thermal barrier coating. So thermal barrier coating means the heat will not actually reach the metallic part of it. So they have a ceramic type of zirconite and different materials they use, and then they coat that. Then the second one is they have the micro holes which are being drilled, and then a coolant fluid will be circulated, and then the heat will be taken away. And then the third one is that this fluid which is flowing on the blades will form a micro layer on the turbine blades and then insulates the heat from reaching even the thermal barrier coating. It is called a fluid film which will be formed. So thus, these are all the things which are required to keep the blades from melting. But now the question is, how do you make these kind of holes? Actually, we have done a project for GTRE, so Gas Turbine Research Establishment in Bangalore, so which they are developing the gas turbine engine, which is called as a Kaveri engine. So if you want, you can type in Google and look for the information. So there are several challenges to make these kind of designs, and one of them is to make these coolant holes in the titanium nickel type of alloys, which are categorized as difficult to machine materials. So to do that, we have actually used what is called as the ultra short pulsed lasers. We have used the lasers. So now, how these lasers work? If you look at them, as the title says that it is fundamental, so I'm trying to give you some of the fundamentals. How the laser will be able to remove or cut the material which is very hard. So literally now by using these lasers, we can cut any of the materials. So how it is done is, when you put the laser beam, so some of the heat which will be absorbed, and then the heating takes place. Then the surface will melt. Then after that, the whole surface will vaporize, and then it forms a flume and a balloon, which will be called as a plasma. And then later, that balloon kind of flume, it bursts, and then the whole molten material is removed. So thus, with this kind of a technology, we can machine any hard material that is possible. And if you look into the history, how these lasers were made, it's very, very interesting. So right in 1900 itself, Max Planck has said that there is a kind of radiation which is possible, which will be able to be emitted by the radiation. And then even Einstein, he has said right in 1917 itself, so the definition or the theory behind the laser production. And then later in the history, if you see, there are several people who developed and contributed for making the lasers what we have today. The laser discovery is actually of a lot of interest, and controversies are there, but still we are not looking into the history, but into the technology. Then if you look at the lasers, there are hundreds of types of lasers which are possible. Actually, we have bought several lasers. So we have what is called as Center of Excellence for Advanced Laser Material Processing. So probably if you are interested, you can actually look into this website. I'll just type.
পুরো 7:50 পর্যন্ত একটা আছে। ব্যাটারি 10 মিনিট।
Let me check and right. So if you look at this, so you can see that when we were trying to purchase different types of lasers, for our amazement, we found that there are several types of lasers, and it is very difficult actually and challenging to select the right type of laser for a given application. So there are gas-based lasers, so there are liquid state lasers, there are solid state lasers, there are semiconductor lasers, so free electron lasers. And then if you go into each of them, so maybe CO2 lasers are very, very popular. You might have seen or heard about them. And then we have Nd:YAG lasers, excimer lasers, Ti-sapphire lasers, like this. There are several number of lasers. And then still, if you categorize them based on the way how the lasers will be coming out, so we can subdivide them into continuous lasers, nanosecond lasers, femtosecond lasers, or we can also categorize them as continuous lasers and pulsed lasers. Okay, continuous lasers and pulsed lasers. In pulsed lasers, we have micro, nano, femto, second kind of lasers. And also lasers are available in all ranges, right from infrared to ultraviolet, or rather from ultraviolet to infrared, and also in the visible range. And one more danger with these lasers is that if you are using the lasers in an invisible range, sometimes by accident, if it falls into the eye, so there are chances that the eye gets damaged. I think one of the leading companies and the person who was doing research, so he visited IIT Madras few years back, and then he was telling he was about to lose the eye because that laser you can't even see, but they'll be powerful enough to burn anything. Maybe in some of the fiction stories you'd have seen or heard about that, like you don't see anything but something starts burning. So that's possible because you can have very powerful lasers in the invisible range. But these days, whenever they make an instrument or a machine, if it is an invisible range, they will have a coaxial visible laser light, so that whenever the laser is fired, we can also see the less energy laser which will be coming like the red light or blue, and we can know that the laser is there. So thus lasers are several categories with several frequencies. And now for our machining, actually we used the latest type which is called as the femtosecond laser. Does anybody know what is femto? What is femto?
It is 10 to the power minus 15 meter, I think.
Yeah, very good. So it is 10 to the power of minus 15. Here it is not a meter, it is 10 to the power of minus 15 seconds.
Femtosecond.
Yeah, so femtosecond. So 10 to the power of minus 15 second.
Okay.
That means we can imagine that when 1 second is divided into 10 to the power of 15 times, so that small part of the second is called as femto. Now, what is femto? If you look at the light, so this is a real-time actual video, so wherein it takes this real time to travel from Earth to the moon. So this is the real time actually for the light to go around the Earth. This is exactly the time what it takes. And to go to moon and then come back, this much is the time. And when it is traveling at such a high speed, the time which is required to cross the diameter of the hair, so that is 1 femtosecond. That is 1 femtosecond. Okay, hope you are able to understand. So when it is traveling with 15, okay, how much is this? 15 crores kilometers. So that is the distance between the sun and the earth, and it can go and come back in few seconds. So when that is the speed, the time which is required to cross this hair, so that is a femtosecond. Thus, when you put a pulse of the laser in that short period, actually there are several things happen. We have conducted several experiments,
স্ক্রিন রেকর্ডিং হচ্ছে মানে তোমার
and in one of those experiments,
তাহলে সেটাও রেকর্ডিং হয়ে যাবে নাকি?
so when you put the laser on silicon, silicon is actually a very highly reflective material. So just put the laser, you know what interesting thing happens? It forms a very systematic kind of a pattern on the surface. So we can't see that with our naked eye, but when you keep it under the SEM, scanning electron microscope, you can see them. So that is called as laser induced surface structuring. That is what actually happens. And if you put even more intensity, so it drills a hole. And in some of the cases, even we could produce the nanoparticles. And in some cases, you know, even to cut the glass, what you need to do is, even if it may be a thick glass, but what we can do is take a laser beam, just draw a line on that. And for a few seconds, we will not see anything. But after some time, we find that the glass will break into two parts. So wherever the laser has passed. You know why? Does anyone can predict why that will happen?
কিন্তু আমার আরো দেরি হয়ে যাবে ব্রেকগুলো নিয়ে আবার সবাই জয়েন করলো জানি না আমি সেটা সেশন
Have you understood the phenomena?
মাঝে মাঝে কোশ্চেন করে
Yeah. Can somebody guess?
Sir, I think the glass is brittle, so maybe the brittle fracture will take some time before splitting off into two parts.
Yeah, that's right. So what is going to happen is when you put the laser light, it initiates actually the crack, and then after some time the crack will spread, and then we find that there'll be the crack, the glass will start breaking. So thus, with this femtosecond laser, so we can have several phenomena which can be happening. There is a small issue which
বড় প্রবলেম হচ্ছে ও দেখছি তিনটে ডিভাইস লাগিয়েছে জিএল সামনে একটা বলছে একটা চলতো কিছু দিয়ে কিছু
So this was the kind of difficulties we used to have in lockdown. So now again we are facing. Okay, yeah. So thus, when you make the pulses shorter, so we see that there will be interesting phenomena which will be happening, and we have hundreds of applications of these femtosecond lasers. So even the surgery, when you see, so the laser surgeries are being done with this, so that even the eye surgery we can make it without damaging the other tissues. So we'll be able to cut the layer of the skin or the tissue without damaging other tissues. And that is also called as minimum HAZ, heat affected zone. And here, one more interesting phenomena what we see here is, usually the laser power will calculate by the amount of energy what we put and divide by time. So here, whenever we give, so this energy what we give is only like few microjoules. and few microjoules. When you give, like, say, 10 microjoules of energy, it is 10 into 10 to the power of minus 6 joules. Divide by time, 1 femtosecond, 10 to the power of minus 15. When you do that, you cancel the zeros and bring the denominator to numerator. So you are still left with 10 to the power of 9 joules. So thus, when you put that femtosecond laser on any material for the fraction of the second, then the energy or the power what you get at that particular place will be 10 to the power of 9 joules. So that is like a gigawatt kind of a range. So thus, it not only melts, but it evaporates any material literally. So thus, whatever is the hardest material, will be able to cut by using such type of lasers. And also when you look at the phenomena of cutting with the lasers, so if you use microsecond lasers, they are called as the pulsed lasers, but femtosecond lasers are called as ultra short pulsed lasers. So here we see that there is a heat affected zone, and also we see that the cut which we make will not be very clean. So this is the way how we get. But if we make them like a femtosecond laser, we can clearly see that it's a very neat kind of a cut. So thus they call these femtosecond lasers as the scalpel of a doctor. So scalpel means the knife which the doctor uses. He will cut exactly the layer of the skin or any tissue or organ. So where it is only required, you won't even cut more. So thus we can see that these lasers will give a very nice kind of profiles. So I'm going to show you later even the profiles which we have cut by using the ultra short pulse lasers what we have. And also when you make the micro channels, so you can see here, so you can see the heat affected zone when you cut with long pulse or continuous lasers. But when you use the short pulses, we find that you get a very beautiful cut like this. So this is another comparison, so which have been made between nanosecond pulses, picosecond. You know what is pico? Picosecond?
10 to the power minus 12.
Yes, you're right. So 10 to the power of minus 12. So then as the time decreases 10 to the power of minus 15, so we find that we get a very clean cut. Now, I'm going to explain another fundamental concept. So if you try to understand, you will appreciate why these ultra short pulse lasers have such a kind of a good effect or good tools for machining. Actually, this diagram was developed by us. We took actually several weeks to draw this, to make the concept and to draw. So why? Because one of my students was doing the PhD and we tried to explain what is the effect of the laser when it is put on a material. And then there were no diagrams, so we developed our own diagram, and this has been published in the journal paper. So if you want, you can look for the name Kiran Kumar, myself, and Professor Shanmugam. So you put ultra short pulse laser, you can get this paper, or later I can give you the link also. Yeah, so what is going to happen is when you put this laser here, so this is the bulk of the material, and usually in the metals, so in the conducting electrons will be there on the top layer. So now when you put the ultra short pulse lasers, so the top layer actually absorbs the heat, and since the time is less, there won't be much time for the heat to go into the bulk of the material. But before that, these atoms or electrons and the plasma which is formed there, it just gets evaporated. So thus, when you use a femtosecond laser, when you cut a material, immediately you can touch. But don't do that when you're using the CO2 lasers or the continuous lasers. You know, if you touch that, it will be very, very hot. But in ultra short pulse laser, you can touch them immediately because there is no heat which has gone into the bulk of the material. So like whichever the atoms, electrons and neutrons, whichever receive the energy, there will be so high intensity that immediately they leave the material and ablate. That's called as ablation. So they get evaporated. So that this phenomena is very interesting. We also actually did the research in modeling it and trying to predict that. So by using a software called COMSOL, multiphysics, but it's not that easy. It was challenging because to get the results at 10 to the power of minus 15 scale, so it takes long time. So even to simulate 2 seconds, it takes hours together. And also the elemental sizes were micrometers and nanometers, because when you put one pulse, the amount of material removed will be few nanometers. So if you had to predict that, obviously the mesh what we take should be in nanometers and even smaller. So thus with nanometer mesh and with time periods of 10 to the power of minus 18 or so. So if you have to capture minus 15, so your scale need to be even much lower. So thus it makes a very big challenge to simulate this, but our student has attempted to make these kind of a simulation, and we were able to predict what is going to happen when you put one pulse of the laser, or if you put 100 pulses, what is going to happen. And another interesting phenomena what we have observed here is, so when you put the laser pulse, so we find that the temperature rises to very high temperature for the electrons. So this is called as electron temperature, and then the lattice temperature, that is the bulk of the material. So the bulk of the material actually slowly gets heated up, but the electron temperature goes very high, and after that immediately it starts decreasing. So at a particular time, so it comes to equilibrium, and within that time, if you can put the pulses, so we can see the machining happening there. Any questions up to now?
Yes, Kaushik Mondal, you can put up your question. You have raised a hand. Kaushik Mondal. You can unmute Kaushik Mondal and you can go for your query. Kaushik Mondal.
Okay.
Okay. So you can continue.
Yeah, okay, fine. So now I'll quickly take you forward. So if you have any questions, you can stop. But now, how do you produce this short kind of a pulse?
Excuse me, sir.
Yeah.
Sir, this is I'm talking on behalf of the organizers. So basically, there is a provision of short 10-minute break. So I mean, I understand it's a very engaging lecture. So if you want to continue, and participants are also, we are fine. So I mean, it's your call, sir.
So you want to just take a small break?
I mean, as per the schedule, there is a small...
It depends upon you whether you want to take a break. It's up to you, sir, or whether you're going to continue.
Yeah, we can take a break now, so that even students can get refreshed.
Okay, sir.
Okay, then we'll take 5 minutes of break.
Oh, right,
Sure,
sir. Right,
sure,
sir.
sir.
Right,
Sure,
sir.
sir. We will
Sure.
we will get back here after 5 minutes. Okay.
So we'll come back after 5 minutes. Yes.
Yeah, sure.
Right, sir. Thank you, sir. Thank you, sir.
Okay. So now we have seen till now that these ultra short pulse lasers are very interesting, and they can touch or ablate any material literally. So now the question is, how do you produce these kind of short pulse lasers? So in the beginning, actually, when they wanted to get the pulse lasers, so they made a simple mechanical kind of a method. So where when the laser will be coming, so they will take a circular disc which has the slots. So that will be rotated. So thus, when the opening is there, the light will come out. So when the blank part is there, when the metallic part is there, the laser will not be coming out. So of course, laser is also light. So thus they used to make, but the problem is that the laser will be high intensity lasers will heat that disc, and then it starts melting after some time. And also high speeds much are not possible, and those mechanical methods are not possible to do. So now we have actually what are called as optoelectronic kind of a methods. So by using which we can produce these kind of ultra short pulse lasers. So one of them is called as mode locking. I don't explain in detail, but just I'll try to tell you the concept where you can understand. I think you would have studied what is called as interference of light or interference of any waves. So when the waves are in phase, actually I thought of drawing them, but when I connect to the pad, it's getting struck. So I'm not trying to do that. So let me try. When you have the waves which are moving, when they are in phase, they will produce bright fringes, and when they are out of phase, so they produce dark fringes. I think this concept you know. So similar to that kind of a concept, we don't give this laser light completely out of phase, but we give them with a particular phase difference. In that case, what happens is, during some period, so there will be a complete darkness, and during some period, so we find that there will be the waves with a high peak. That is, both destructive and constructive interference will be taking place. So resultant of that, what we are going to get is the high pulses during a particular period, then there is no pulse, then after that again high pulse. So that depends on what is the phase difference which we are going to give. So that this is one of such kind of a method. Then there is one more interesting phenomena which is called chip pulse amplification technology. Why we need this kind of a technology is we need to pump a lot of energy into the pulse. So then only we'll be able to remove the material. Actually, today we were working with our laser, with a femtosecond laser, and then we were finding that we are not able to machine the material. Why? Because the laser is coming, but this high energy is not pumped into each of these pulses. How do you do that? It's a very interesting optomechanical, optoelectronic kind of a phenomena. So wherein we take a laser pulse of this particular width, and then we pump, there are lasers which are called pump lasers, then make that energy big. So make this energy. So then pass through other optics so that you compress the width of the wave. So in the time scale, in that case, what happens is the intensity becomes more. The energy which was there in whole of this pulse, so will be packed into a very short period, but intensity will be high. So thus this technology is called a chip amplification technology. So we make the period of the pulse smaller and at the same time pack high energy. And that is the reason why these lasers are very, very powerful. Now coming to the applications of these kind of lasers. So we can, as I have already said, to make that coolant holes, so we can make them. So this is called as laser micro machining. Okay, so the first one should have been micro drilling. So wherein we can make the small holes in literally the hardest materials. So these are some of the features even we have done these kind of holes. And there are three methods of doing that. So first one is called as a precursion drilling. Precursion means just put the pulses. Then the diameter of the hole will be of the order of the spot diameter of the laser. But if you want a bigger hole, so we use the method what is called as trepanning. So where we make the laser beam to go around the diameter or the perimeter of the hole. So then we remove the material. So this is called as trepanning. But then if the thickness is more higher, we go for what is called as a helical drilling. So it not only goes around, but at the same time it moves to the higher levels so that the material can be removed. Or rather we can move down so that the thick materials can be drilled. So we have used these kind of technologies to produce the micro holes for the coolant, for the micro coolant holes in the turbine blades. And now, by using laser, it's not only drilling, but also actually we can mill the surface. So milling means, I don't know if you have heard a term what is called as texturing of the surfaces. So we want different types of surface. So that we can do it by using the laser milling. So you put the laser, the top layer of the material will be removed. And then you scan the whole of the surface, by like a raster scan. So you can remove the material. So this is called as laser micro milling. So you want to make a channels or you want to modify the surface. So we can do that by using these kind of phenomena. Okay, so these are the details about laser percussion, laser trepanning, and one more interesting mechanism is there, and that is called as drilling on the fly. Drilling on the fly. See, when you look at these turbine blades, there are hundreds of these holes which need to be machined, and there are several blades and hundreds of the holes in each of the blade. And then what we have said is that when you send the pulse in a femtosecond, this is the pulse. I'm not able to draw it perfectly. And then there will be a gap, and then the second pulse will come like this. So if you take in the time scale. Now, how do we utilize this time between the pulses? So time is very important in production. So thus, they wanted to utilize the time between these pulses. So for that, what they do is, you have the turbine blade, which has the capability to rotate. So mount it on a motor, and then make the pulse to fall first on this blade, okay? Say 1. Then, by the time the second pulse comes, instead of wasting time, you move this turbine to this position. So then the second pulse will fall on this. Then the third pulse, 4. So thus, on one side, you find that the turbine blade is rotating at high speed and the pulses will be falling, and several holes can be drilled right in 1 second in several of the blades. So that's the way how they produce hundreds of holes. But there is a lot of synchronization which is required to the speed of the rotation of the blades and the position where you want to drill and the time gap between the pulses. So we have what is called as a pulse frequency, so where we set number of pulses. So usually the pulse gap between the two pulses will be more longer than the period in which we put the pulse. Okay. So for example, if 10 femtoseconds is the pulse width, so then the gap of 50 femtoseconds or 100 femtoseconds will be given. So like that, we can utilize even the time gap between the pulses. I think this already I have explained. So by using this kind of a phenomenon, we can even drill the holes. And the next application of these lasers is welding. So where if you look at the welds, day before yesterday, one of the professor who came from France, he Central Institute Nantes in near to Paris. So he was telling how they use this laser welding technology in ships. You know, in shipbuilding, there are several thousands of kilometers of length they need to weld. Thousands of kilometers of length welds will be required. So by using lasers, we can do that at a very, very high speed. And also, welding of dissimilar materials is also possible by using the laser welding process. Then the next application in machining is we can have what is called as laser assisted micro machining. So it is called LAM, laser assisted micro machining. So one of the professor Mailkote, so he's an Indian, so he has been working on this area. Now he's in US. So wherein by using the laser, we can heat the very hard material before the tool comes into contact. So as the tool is moving forward, so the laser will move just a phase before that and keeps heating, and thus we'll be able to remove the material more easily. So this kind of machining is required when you are machining what is called as difficult to machine materials or hard materials. So when the BHN is above 50 and all, it is very difficult to machine with the conventional processes. But by laser heating, followed by the cutting tools, and usually it can be like CBN tools, cubic boron nitride tools, so where we can remove the material very easily and get a very good surface finish. And also, the heat affected zone is one of the important factor which we need to consider when you are going to machine with lasers. Nowadays, actually what they are doing is to reduce that heat affected zone, the machining takes place under a media, and usually that can be water. So where you put the workpiece inside water, but focus the laser on the surface of the metal. So then several researchers, including us, so we have tried that and then found that the cut is much better when compared to an oxygen environment like air. And if you look at some of the applications, so in inkjet printers and all, so this jet which will be coming out from these nozzles, so the smaller the holes, the finer will be the print. So thousands of such holes will be required, and we can make them by using lasers. Not only that, we can use these lasers for making the holes in the fuel injectors. So wherein in the nozzles, so we find that we need very, very small holes, and the material usually will be very hard because I should not get worn out during the operation. So thus hard materials and small holes which are required, small diameter holes. So in that kind of a case, so laser is the best option. And another interesting area where lasers are being used is biomedical applications. So usually I think you would have heard about what is called as stents. You know, in the heart, they put these stents. So here you can see, you know what they do is, when they are sending these stents into the arteries or into the part where there is a blockage. So think that there is a blockage, something like this. So we compress this stent like this, it will be small. So then it will be made to enter into this place, and then it will be made to expand. So it expands and then makes the way for the blood to flow. So that's the structure which is required for that can be cut by using lasers. So thus it may be nitinol or stainless steel or cobalt chromium or platinum chromium. All these alloys are very difficult to machine, but we can machine that by using the lasers. So then they can be put inside the heart, and we can remove the blocks or make at least the blood to flow properly. And even in the area of automobiles, nowadays we use the laser welding. So wherein the spot welding, the continuous weldings which are required will be done by using lasers. And not only that, we can see some more interesting types of surfaces which we can produce. We call them as what is called as functional surfaces. So textured surfaces or functionalized surfaces. You know, if you have seen the lotus leaf, when you put water, it doesn't wet the surface, but beautiful spherical water droplets will be formed on that. Does anybody know why that happens? Any idea? Yeah, when you put water on the lotus leaf, it doesn't become wet, but it becomes a beautiful water droplet. Why? Any answer?
So due to super hydrophobicity, I guess.
Yeah, that's right. So what is hydrophobicity and what is super hydrophobicity?
So it depends on the contact angle. Basically, it depends on the two substrate, that is liquid, solid, and air. Its characteristics. So if the contact angle is, I think, greater than 125 degree or so, it's super hydrophobicity.
Yeah. Okay. So does everyone knows that, or? So everyone knows that? Okay, so thank you, sir. I think you are given correctly. So what is going to happen is this surface has beautiful micro pillars. Okay, so they have beautiful micro pillars. They'll be very thin. And when you put, usually like if it is a plain surface and when you put the water droplet, so it will be like this and then it gets wet. But when you put the water droplet, okay, I think I didn't draw it like this. So they make this angle larger and then thus a spherical surface will be formed. So this is natural on the lotus leaf, but we can make that kind of pillars and texturing on the surfaces by using lasers. So one of my students has worked on lasers texturing of the tools. So we use the drill bit. So both on the clang surface and also on the flute surface. So we have textured, and then when we machine by using such kind of a tools, so we find that the cutting forces were significantly smaller than without these kind of textures, and also the efficiency increases, so the energy consumption comes down, and the surface finish what you get was much improved. So thus texturing of these surfaces with either micro dimples or micro pillars, and so they help in several of the concepts. So why here the friction was reduced is that when you make a micro dimple texture, so the microfluid actually goes into that, and then there'll be a film lubricant which forms and reduces the friction. So I think you know in metal cutting, so the friction is the cause for heating and also for wear. So thus, if you can reduce wear, so you can reduce the cutting forces, you can reduce the tool wear, and you can make the chips to flow much smoothly, and thus our machining process will be very highly efficient. So thus this phenomena of texturing plays a very, very important role. And also in the aircrafts, so when they are in the cold atmosphere, usually the snow will fall. And when the aircraft is stationed in the on the tarmac, so actually there will be a big layer of snow which will be falling, and that is actually very dangerous. And there were many accidents happen because of that kind of a snow formation. How do you avoid that? So for that, what we can do is we can make the structure so that the ice or the water or the snow which falls will not get stuck to that, but it will slide away. So thus you can make the surfaces hydrophobic or super hydrophobic, so that the ice or the snow will not get deposited and we can avoid accidents. So like this, there are several phenomena which will be happening.
Sir,
yeah.
Sir, actually, it's like you're increasing the surface area.
Yeah.
At the micro level.
Yes.
Right. So in case of cutting tool also, when you are making those micro insertions and making the holes for enabling the fluid to get inside, as well as you are making those grooves in femto level. So basically you are increasing the surface area, and that is also enabling the cooling effect of the tool and on the surfaces also at the femto level. So that also releases the heat during the metal to metal contact, thereby reducing the frictional force. Right, sir?
Yeah, you're right. So actually there are applications which are called as micro heat exchangers.
Right.
So where heat transfer is the main important phenomena which need. So there the surface area plays a very important role. So as we know, when you make the fins, so why do we make the fins? To increase the surface area. So the more the contact, so the more heat will be taken away.
Right, sir.
So thus in micro heat exchangers, so we use this phenomena of increasing the surface area by using these textures. You're right. Yeah, thank you for adding that kind of a point. So I appreciate that. So others also, if you have any more points, you can add. And I'm very glad that you're well informed. And that is the reason initially I asked who are the participants, so which level. So you are at a very high level, so I could just move on with these concepts. So otherwise, if somebody doesn't know anything about lasers, if you tell all these things, they won't be able to appreciate. Okay, so thank you very much. So this is actually the kind of a setup what we have developed here. So this is actually a hybrid type of machining setup. So this one is micro EDM setup with a rotating spindle and the micro wire, micro rod will be used here as the EDM, and we drill the holes. And this setup is actually the femtosecond laser setup. So where we have the what is called as F theta lens. So by changing the lens, actually we can make the ray to move in X and like in both the directions, X and Y direction. And then by using this stage, we can move it in vertical direction. Okay. So thus three-dimensional movement we can make, and then we can machine the features. But now, why did we make this as an hybrid process? It's because, see, usually when we talk about femtosecond laser, it's a very neat and a precise cut, but the material removal rate is comparatively lower when compared to picosecond, nanosecond and microsecond laser. Then how do you compensate it? So thus we know that EDM is one of the most popular machining process which have been used in industry. So now you go to any industry where they are machining hard material, they will have wire EDM there. So thus, here the material removal rate is not as high as compared to the conventional machining, but it is quite big enough. So thus, when you want to make the micro holes, first we make a hole by using iridium and then send that blade to this and finish it with the femtosecond. So thus, we can get precise holes and also have a higher material removal rate. So thus, this is an hybrid process which we have developed. And another interesting thing, we had actually a laser with a older generation where the size of the lasers used to be very, very big. So the equipment which is required to produce the laser will be very big. But now in our case, so this is a fiber-based laser, you will not able to see the whole picture, but only this much. It is something like a scanner size. So we are able to produce such a powerful lasers by using such a small equipment, and that is possible because of fiber. So wherein earlier, like there used to be full reflective and partial reflective mirrors, and this will be the length. So we need something in terms of like meters. But now, because of the fiber, you can put that in a small space, and that is the reason you get very compact laser source. And actually, our equipment has an inline camera. So when we are machining, actually, even we can record how the machining is taking place. So here we have given slower pulses so that we can see the pulse. The gap between the pulses is very small, large actually. And we have machined different types of holes, but still there is a challenge with the laser is that when you produce the holes, they are not very cylindrical like this, but they are like this because these are micro holes, and even there is no space for the light to enter here. I think we know that light has a wavelength like this, so there won't be even enough space for the light waves to enter, and that is the reason in the front side we see the hole shape like this, but on the back side, so we find that the holes are not of the required diameter. But we can use the other methods like trepanning method or helical drilling to overcome these kind of holes, these kind of challenges. So we have characterized them by using several technologies. So by using SEM, or we have actually the 3D profiler, so by using which we could measure the profiles. Also, we have actually characterized these features by using the LSM. So what is LSM is laser scanning confocal microscopy. So we can use the laser light to go into the micro holes, and we can actually characterize them. See, why we are telling this is it's very, very challenging. Yes.
Sir, in the previous slide, you have shown that the holes that were drilled are having tapering effect.
Yes.
And that you are overcoming by trepanning.
Yeah.
Okay. So this tapering effect and the overcut that you are having on the top surface, you are eliminating by using the trepanning method.
Yeah, actually, but still there is a challenge. If the diameter of the hole is equal to the spot diameter, so we can't do trepanning. So what
there will be overcut if the diameter of the hole is same as the spot diameter. There will be overcut.
Yeah, but what we are making is actually they call it as tight focus. So where if you can make the spot diameter as small as possible, so then we can actually make that light to go around like this, and we can remove the material. So this is trepanning.
Conventional technique calls it as a boring operation.
Yeah.
Enlarging the hole.
Yes.
Enlarging the hole slowly.
Yeah.
Okay, sir.
So here we send the laser light along the periphery of or the circumference of the circle.
Thank you, sir.
Yeah. So actually, why we did all these things is that, as I said, we wanted to understand what is going to happen to a material when you put only one pulse, and the amount of material which is removed is few nanometers. How do you characterize them? It was so complex and it was challenging. By using different methods, we tried to characterize it. So the laser scanning microscopy is one of the best option. But then when the sizes were even smaller, we used atomic force microscope. So the bottom side, what you see is the real atomic force microscope image. So what we have taken, and then we tried to characterize. So we gave the profile. I don't know whether it is clearly visible or not. So it will be something like, so here it will be like this. This will be the profile of the hole. So then we tried to see what will be the depth, what we get when we put 1 pulse, 10 pulses, 100 pulses. So that phenomena is called as laser matter interaction. So you put a laser, how the matter is going to react. Okay, so even when we tried to characterize with that, we couldn't exactly get the profile because when the size is small, so the light won't reflect properly, the tip of the AFM will not be able to reach. But then what we did is actually we cut the micro hole into half. So that is actually carefully use the emery paper, hold the workpiece, slowly remove the material because the size of this is only few micrometers. So you can see here, it's only few micrometers. So then try to stop it exactly at the middle and then take the images. So it was not possible with one, but several images we took. And this is where you could exactly see the depth of that micro hole which we have produced. So this is called as the characterization. And okay, there are several temperature and other things where we have done the research, but probably we may not look into those details. And only one thing you can see that when you put the first pulse, the temperature will be at room temperature. But when you put the temperature subsequently, actually the temperature increases. So thus the effect will be even different. When you put 5 pulses, it will be different. When you put 10 pulses, it will react differently. And when we made these cylindrical holes, we had another challenge. If it is a smaller depth, we could measure by using the methods which I have told. But if the depth is high, we couldn't actually see the whole cylinder. So then in IIT Madras, we have a facility which is called as CT. So CT is similar to the technology what we have in our scans. So it is called computed tomography. So where when you go for a scan in the hospital, they do similar to that. And then we have micro CT and nano CT. So where we can send the X-rays and the cross section of these holes, and we can actually get the whole of the cross section of the holes without damaging. We'll be able to see the 3D holes. So finally, by using the other geometric softwares, we could get the cylindrical part of the holes. So this is possible only with CT. So other technologies, we can't get this kind of a cylinder and we can't evaluate the cylindricity. But by using the computed tomography, nano CT, so they take layers and layers of these images and then put them together to reconstruct the actual holes. So thus, it is a challenging process. So we have characterized them by using this. So these are the details about micro machining, ultra short micro machining, and characterization. Thank you for your attention. If you have any questions or doubts or anything you want to add, you can do that.
Thank you, sir, for your engaging lecture. Dear participants, if there is any questions or query, please go ahead.
Sir, I have a query.
Yeah.
Like in this laser that you have shown, is there any material deposition on the surface of the holes that you are generating,
Yeah.
like recast layer?
Yeah.
There will be
Yeah,
certain amount of
actually,
small amount of microscopic recast layer that will be there, I hope.
yes, yes. But actually, it's a very interesting phenomenon, as I said. You know, when you are trying to put make the holes, the holes what you produce, actually the shape will be something like, okay, so I couldn't draw it because I'm
Right,
drawing
right,
it with hand. So there'll be two caps here.
right, right, right.
And how that interesting kind of thing. So it will go like this, then this will be the hole, then it will be
Right, right, right.
like this. So here we have the material flow which will be coming there. And also there will be small amount of molten material
Right, right.
which get stuck there. So that's, it won't be completely perfect, but when you magnify higher and higher scales, you can see
Right,
this
right.
phenomena.
There will be certain amount of recast layer, right?
Yes.
So, is there any way that you can possibly eliminate, or physically you have to use another method of surface polishing?
No, actually, what we do is, see, when I showed you the profiles in the beginning to compare this phenomena, you can see that this is the way how it will be. See, now when you use continuous laser, this will be even worse.
Right,
So with
right.
nanosecond, it is like this. With picosecond, it will be like this. With femtosecond, it will be like this, which is literally good enough
Right.
for any practical purpose to directly be used.
Sir, don't you think that there is a limitation of femtosecond pulse, because if the thickness is large, then of the work material is large, then it will be difficult for using this femtosecond pulse for making a larger depth of hole.
Yeah. See, smaller diameter and larger depth will be very difficult. So we call that as aspect ratio.
Right, right, right. If the
So that
aspect
L
ratio
by
is small, then it will be very easy for femtosecond pulse to apply.
Yeah, yeah.
Right, right, right. Okay, sir. Thank you, sir.
Yeah, thank you.
Any other question?
Any other?
any other question actually বলেছি উনি আর আমি দুজনে একসঙ্গে any other question বলেছি তো কি end করে দেবো if there is no
Sir, one thing, like in laser, we know there will be certain amount of heat affected zone. Whatever possible method you apply, like in case of the laser you are applying underwater or under some chemical liquid, so that will be minimized. But in open air, when you are using this laser, there will be some heat affected zone which will be actually damaging the intercrystal lattice, right, sir?
Yeah, yeah.
So I think in femtosecond that will be minimized according to your deliberation, right?
Yeah, that's true.
Okay, sir.
Okay. Yeah. Any other questions?
Any other
Okay,
questions?
sir. No questions, I hope.
Okay, so if there is no other question, so let us thank Professor Samuel for such a wonderful lecture. I hope that participants have been enriched through his deliberation. So if there is any further query, you can reach out to us. And moreover, we'd like to mention that there will be a feedback form regarding the today's session that will be shared in your WhatsApp group. Please fill up that form in due time. So thank you once again, Professor Samuel, for the wonderful lecture. And
yeah. Okay. Thank you. And
Professor Samuel, it was wonderful hearing you with all your detailed experimental results and illustrations. It was really nice, sir.
Thank you. Thank you.
Yeah. So I am Professor Bose. So I'll be visiting your place sometime soon.
Yeah.
It was nice having you with us. It was very nice having you with us, and we really enjoyed the lecture, and it was very interesting. I was keeping my eyes open and seeing all your work. It was really a wonderful job that you have done, sir. Really, hats off to you, sir.
Thank you. Thank you.
Thank you, sir. Good night, sir.
Okay.
Yeah, thank you. Good night. Wish you all the best. Yes.
Thank you, sir. Thank you.
Thank you, sir. Okay, so we have come to the end of our first day of the FDP. So we should join here same time tomorrow for the next session of expert lecture. Thank you. Good night all.
Good night.